Hello. What about it? Locked it for the, is it for the assessment or something? If it asks for it, I guess. I don't know anything about, so the assessment's open, right?
Yes, it is.
Okay. Whatever it tells you to do, I guess you got to do. So yeah, that's the first thing. I guess the assessment thing is Tuesday, and I guess it is open, so that's good. So if you do that, that'll factor into the grade at some point. That's be one of those, they send me a list at some point, I add the grades. Yeah. I think each one's worth 1%. If you do the second one, you get 1%, you do the first one, you get 1%, you do both, you get 2%. Yeah. So it's extra credit. It's purely, so the assessment thing is purely extra credit. I have no idea what the questions look like. I have not had any impact on the questions, so I can't promise they look anything like what we've done in, I know nothing about it. Hopefully it looks okay. Here we are, y'all. 2 more classes, today and Monday. So my thought processes for today, we'll talk about what was on test 1, and I'll specifically focus on the questions that a lot of people missed. So we'll talk about those, and then Monday we'll do what test 2, what people missed, but there wasn't really as much for that. And then, that's it. I mean, if you all have any questions at any point you want me to do, we'll kind of do them, but at this point, should be pretty good. All right, so test 1. What was covered on test 1? So, reminder to you all, and I mentioned this last time, I am not making a overview for the entire final because I've made them already. They exist. If you go to test 1, there's an overview for test 1 material. Test 2, there's an overview of test 2 material. And then in the final, I put the rotational stuff. So there's 3 PowerPoints kind of covering everything. Great checklist. Go through them. If there's a single thing that you're like, what the heck is that? You should do those kind of problems. Otherwise, let's go ahead and jump into what was one of the things that a lot of people missed on test 1. So one of the things, so test 1, just a reminder, was kinematics. Kinematics, circular motion, a little bit of circular motion, and vectors. I think it was mostly kinematics, vectors, and forces. Yeah, we did forces on test 1, right?
Yeah, so we basically, everything we covered, work was the first thing we covered after test 1.
Yeah, okay, so test 1 was mainly kinematics and forces. Kinematics, forces, and circular motion. So one of the ones that people missed, and this, so any of the specific questions that you all missed from previous tests, you can almost guarantee there'll be one like it on the final. So these are the only questions that you're almost like guaranteed. So the problem on the test 1 that a lot of people missed was a car is going around a roundabout. Let's make it more clear in case you don't know what a roundabout is. A car is going in a circular path with a radius of 10 meters. How fast can the car go if the coefficient of friction is 0? I don't care what the number is here. It depends on the problem. All right, how fast can the car go if the coefficient of friction is 0.8? So, see if you all remember how to do this. See if you have an inkling of how we're gonna go about this. There's a couple key things I mentioned here. All right, so as always, a picture is going to help us understand this. And the two key phrases here are circular path and friction. We're going to need both of those ideas. So something goes in a circle. Remember, anything that goes in a circle experiences an acceleration towards the inside. That's what keeps it going in a circle. And then you remember that there's two ways to get that. One, you have to ask what force is keeping this thing in a circle. So what force is keeping this thing in a circle? Friction. There's a friction keeping it in the circle. That's why it doesn't slide off the road. If friction didn't exist, there's no reason for a car to stay on a turn. Hence why icy roads and stuff are dangerous. You take a turn, you got no friction, you'll keep sliding. And then you remember that if you're going in a circle, all the forces, sum of forces, if you're going in a circle, equal mv squared over r, the centripetal force. So, this problem, and you can expect a few of these ideas. I didn't ask really that many on test 1. But the idea of the net force equaling mv squared over r is a very, very, very handy tool. So like another, well, we'll finish this one and then we'll talk about it. So, long story short, force of friction equals mv squared over r. What is the force of friction? Mu mg equals mv squared over r. If you looked at this problem and you're like, but you didn't give us the mass. You don't need it. The mass didn't matter. Now, in the real world, it's a bit more like mass matter. Mass doesn't matter so much as the height of the vehicle. So if you're traveling in a vehicle with a really tall, you also have a torque going on, and so that's what causes cars to tip over. It's not common for cars to slide off roads. It is common for cars to like flip if you go around a turn too fast, because we're not accounting for torque here. There is a rotation that you have to account for, but not you all, but like if you're doing this in the real world. All right, so great, really straightforward. It's just algebra at this point. But this here, f of a circle equaling mv squared over r, that is a very important skill for you all on this upcoming final. I didn't ask a ton of questions about it. This was one of the questions I asked on the test 1. And we had quite a few people miss it, but if you all go to the problem set from test 1, I highly recommend making certain, so if we go to test 1, problem set 1, the problems at the very end are important for you all to know. I mean, you know, all these problems are important, but specifically, application, yada yada, all these circular motion ones, y'all. Look at that. Here's what is the maximum speed? Bam, right there. Hey, here's another one, but instead of it being friction, it's the normal force and gravity. That one's not a big deal. Don't worry about that one still. You do not need to worry about number 9. That one is overkill. Feel free to try to solve it if you want a challenge, but that one's a little overkill. And you also don't need to worry about number 12 and number 13. But, long story short, number 10 and number 11 are good problems to make certain you know how to do. Circular motion and relating the forces that go inwards to the centripetal force. That's really, really important that we can do that. Yeah?
This is the exam overview.
Yeah, this is problem set 1. Problem set 1. Yeah, this is problem set 1 at the very end. So that was one of the problems that a lot of people missed because it was near the end. You know, it was like a tiny little piece, the circular motion stuff. But because we're at the final now, I want to make certain we're good with this because circular motion, like forces equaling mv squared over r, is a pretty important skill. Again, lots of things go in circles. I'm looking up what other questions I kind of need to talk about. That was the major one. That was the main one that most people missed. Let's see what the second one was real quick. 5 and 18. So, look through those. The other problem that a lot of people missed, I'm pulling up on the testing here so I can see it. There's only 2 problems. Again, you all have done pretty solid, which makes me feel good about myself. Alright, cool, that was one. The other one was... and this is also on the free response. Yeah, this is a good one. Okay. So the other problem a lot of people missed was a car, how do I want to put it? Do I want to put it exactly the way it was in this? Yeah, sure. A car starts at rest and accelerates to 20 meters per second in 5 seconds. If the force due to air resistance and friction is 1,000 Newton, let's do a little bit lower just so I don't run into any problems. If the force due to air resistance and friction is 100 newtons, what is the force pushing the car forward? So try this one out, y'all. See if you remember how to do this one. This one, just as many people, these are the only 2 questions that less than 50% of people got correct. These 2 ones. On test 1. So we can draw a picture. Make certain you're good with your free body diagrams. That's still a skill we 100%, 1,000,000% need to be good at. A lot of you all be taking statics next semester, whenever that you decide to do that. A lot of free body diagrams. Net force is 0. All right. Yeah, see if y'all can do the free body diagram before I start drawing things. I don't want to give too much away. See if y'all can do the free body diagram correctly. Be careful. There's some forces that people like to forget to put on these things. Alright, so there is a force pushing the car forward. We'll just call that applied force. Call it whatever you want. Force engine, force applied, force wheel, I don't care what you call it. Call it whatever you want. There's an applied force pushing it forward. There is a friction force pushing it backwards, and it is smaller. The size of these arrows matters a lot when you're drawing these pictures. And the applied force needs to be bigger because it's accelerating forward. It's getting faster, so that one better be winning. If you leave your picture like this, you're missing 2 forces. And you best believe if I ask a free body diagram problem, and I give a problem like this, you best believe this will be one of the choices. And it will be wrong. Because there is gravity, and there is a normal force acting on it as well. You can't forget that those exist. Even though you know they're going to cancel out, we still need to draw them on there to make sure we know they still exist, because it's really easy just to forget that they exist. And those become, if this thing starts going up a hill, those start to matter. The normal force will become bigger than the gravity force, allowing the car to go up the hill. If you go down the hill, the opposite will happen. So those are equal in size, cancel. But we need to at least recognize they're there, even though they will cancel. In the free body diagram, you put all the forces, even if they cancel other ones. All right, to that end, we're going to calculate the acceleration. Well, okay, so using this, F net equals ma equals, now in this case we do have to do x and y components, but like I mentioned, the y components are going to cancel. So when it comes to the y components, F net equals 0. It's not very exciting. We don't need to do anything. But in the x component, we're going to add, so it'll be FA plus negative FF. FF is left, FA is right, so you got to make certain you account for that. Vectors, positives, negatives matter a lot. Okay, so we look at this. We are trying to find FA. We have FF, so that's easy. Well, I didn't give you the mass. Let's put the mass here. We do need that. A 500 kilogram car starts at rest. Great, now we got the mass. If I didn't give you the mass, this problem would be impossible. Good news, y'all. I can guarantee you every problem is possible because I had to make the solutions. One of the fun things you don't get to see, the free response problems, it's actually possible for me to make a problem that's impossible to solve. Because I can make a problem and then I didn't solve it and didn't realize it's not possible. The multiple choice, I can't run into that problem as much. That's a little behind the scenes. That actually happened on test one. One of the versions, I had to go back, and some of you in this room may have had a version of a free response problem where I scribbled out a number and put a new number because it was impossible to solve. And I realized that after I printed it. Only 1 in 3 of you got that version. So you may never even noticed. But anywho, we got mass. Yeah, these should be streamed. Yeah. All right, so we know the mass. More colors. We don't have acceleration yet, but that's really easy. Acceleration is the change in velocity over change in time, assuming a constant acceleration. So it'll be VF minus V naught divided by T. You can look through your formula sheet and kind of make that happen. You can also just recognize that conceptually. You also probably could have just guessed this was the acceleration. 4 meters per second squared. That is reasonable. Yeah.
So you can cancel out mass and solve for the coefficient of friction, couldn't you?
So the question was, can you cancel out mass and solve the coefficient of friction? Not quite, because the FA isn't a function of mass.
Oh.
Yeah, so that's the problem here. You can't cancel out mass because while FF is mu mg, there is no equation for the applied force because that's like a supercar. Why is it getting pushed forward? You got the tires and all that jazz. So that's a great question. Yeah, alas, we cannot cancel mass here, so we needed it. So we have the acceleration. So now at this point we have 4 times 500 equals FA plus negative 500. And this is where a lot of people will make the mistake. And so I'll mention this in a second. There was a free response problem like this. And a lot of people, I think, made the mistake of taking the net force and subtracting the force due to friction. Because they took this acceleration of 4 meters per second squared, they took that as the acceleration that the applied force is doing, and that's not the case. The acceleration in this problem is the net acceleration. If there was no friction, and the wheels could somehow still push this car forward, which wouldn't happen, but if there was no air resistance, this car would accelerate faster. If there was no air resistance, this car would accelerate faster. So long story short, FA is going to be 2,500. It is going to be bigger than the net force it experiences. It is going to be 4 times 500 is 2,000. The applied force is bigger than the net force. The applied force is bigger because it has to fight friction. It has to fight friction. So that's a really important thing to recognize here. If you're pushing a box, you're pushing with a force greater than it is experiencing as a whole. Because friction fights against you and cancels out some of that force. So it makes sense when you think about it a little bit. But it is very easy. It is very, very easy in this problem to find the net force, think that's FA, and do 2,000 plus negative 500 and say the applied force is 1,500. It's very easy to mix these things up. So be careful, write things down. Yeah.
Isn't it 2,000? 500 times 4.
4 times 500 should be 2,000 plus 500.
Oh.
Yeah, let me write out the last step just so there's no reason not to. So this is 2,000 equals FA plus negative 500. So FA, I will make room. So FA is going to equal 2,000 plus 500. So the applied force, and yeah, that's the key here. The applied force is not the net force. The applied force is not the net force. The applied force is the one that the engine uses to make the car move. And that is counteracted by friction. So FA equals the 2,000 plus that, which is 2,500. So again, this is a really good problem to work through. Try it out on your own. That's going to be the way to determine whether you understand it. I will upload these slides with everything worked out. Something you can do with these slides is you can hit review, you can hit hide ink, and everything disappears. And then you hit the button and it all reappears. So remember, whenever you're practicing, do it without my solutions blatantly in front of you, to make certain you can get that final answer and figure it out. But yeah, this is a really good one, and it's just it's a really tiny thing that catches people off. But if you're just careful, you won't make the mistake. If you're just careful and you realize that applied force is not net force. Applied force is not net force. And you can see that in this picture. FA is not the total force. The total force is this plus the other one. So the net force is actually this green arrow. We generally don't draw the net force on here. The net force is that one. It's FA plus negative FF. It's a little smaller because friction cancels it out. All right. Cool. It's a good problem. Mathematically very easy, but also very easy to mix things up and make a silly mistake. Okay, those are the two main questions. So now, let me remind you all what the free response questions were from test 1, because that's another good indication of what to expect in the final. The free response problems I pick are ones that represent the most important things you need to know. I can only pick 3 problems for the free response, so I'm going to pick the ones that are the most important. So, what were the free response problems from test 1? The first one? Oh yeah, go ahead. There is no free response in the final. So this is more just you can't look at the old tests, so unless you have it memorized what was on the test. This is just, hey, here's an indication of really, really important things. In case you forgot what the free responses were, this is my kind of reminder. This is my way of compromising since I did not upload the test for you all to review after the fact. This is my way of compromising that. Alright, so what was one of the problems on it? This will be a good check of your memory. See if you all remember the 3 problems as we go through it. The first one that I remember, projectile motion off a cliff at an angle. So the problem I gave you all was someone throws a ball at an angle of, who cares what the numbers are, at an angle of 25 degrees with a velocity of 5 meters per second off a 30-meter high cliff. These problems are so easy to make. It's so easy to make these problems. Alright, how far does it go? And how high does it go? Now, there is a shortcut equation for the height and the range. There is a shortcut equation, and you may have written it on it. Only the height equation works as a shortcut here. The range equation will fail you, and that's why I warned you all those shortcut equations, they're useful. But the reality is I don't use those equations ever because it's more likely I'm going to make a mistake. Anytime there's like a shortcut equation, you run into the problem of you have to know when you can use it, and it's usually for very specific circumstances. Yeah.
It starts and lands at the same height.
Yeah, you can only use the range equation when it starts and lands at the same height, and this one does not do that. So yeah, you can use the height equation because that kind of works no matter what. Well, that one works as long as the thing's going upwards. If this would be really easy. I would not do this. If I asked you how high something, what's the maximum height someone reaches for someone that throws a ball downwards, the height equation won't really work because the max height is the height you start with. But I wouldn't be meaning to do something silly like that. I don't say that sarcastically. I'm not going to do that. If someone's throwing a ball, they're throwing it upwards, and my problems. All right. So how high does it go? How do you solve this problem? You break it into components. You figure out what's limiting the time. It's the y component because it's going to hit the ground. And there's so many things with projectile motion, so many little tricks to help you this. So let me just list all the tricks. So, I will remind you, you have to break the v into vx and vy. So vx will equal 5 times cosine of 25. These are initials. Vy initial is going to be 5 times sine of 25 because of trigonometry. There's my 5ms. There's my angle of 25 degrees. And I'm asking how far it'll go from the base of that thing. So great, you got to remember to do that. And then the tricks you need to remember. Couple things. Very, very important. We are assuming no air resistance because this problem would be impossible for you all to solve otherwise. Yes, this problem would be impossible for you all to solve otherwise. Double checking that in my head. Okay, so something I want to point out. What's one thing? Vx initial is also Vx final. This thing travels the same speed in the x direction the entire time. Gravity does not affect things in the x direction. If I toss a ball and its x component is 3 meters per second, at every single point, the velocity in the x direction is 3 meters per second. That's really important to remember. That's really important to remember that gravity doesn't affect left, right. Makes sense when it's stated, but it's easy to forget that. The x component of velocity is the same the entire time. The entire time. You want to know how fast it's going to the right in the beginning? Boom, it's that. At some later point, how fast is it going? The same. How fast is it going at the bottom to the right? The same. Its x component of velocity is constant. Vx is constant because there is no acceleration. The only reason things speed up or slow down is there's an acceleration. And in the x direction, after it leaves our hand, nothing is affecting it. No air resistance, stuff like that. All right, that's something you need to remember. The other thing all has to do with the y component. All has to do with the y component. One of those things is that Vy top equals 0 ms. At the highest point, it is no longer moving up or down. At the highest point, the velocity at the top is 0. Really handy. Very, very important to remember. The velocity at the bottom is not 0. That's one thing that people classically fall into. Yes, when something hits the ground, it stops. We always consider right before it hits the ground. We always consider right before it hits the ground. If I say how fast is it going, I would say right before it hits the ground. Because obviously it hits the ground and comes to a stop. And that's its own physics problem in of itself. How long does it take to stop? All that jazz. I haven't taught you all that because that's complex. You'd have to know so many variables. What surface is it hitting? Is it deformed? It'd be disgusting. I've never had a problem with that. So, great. You need to know the velocity at the top is that. This is potentially helpful. If we call this Vy initial, and at this spot here, let's call this Vy1. I don't know what else to call it. When it reaches the same height, that it started at, see if you all can figure out what its velocity is. Vy1 at this special spot, not the ground, but when it reaches the same height it started with, What is Vy1 going to be? It's going to be negative what you started at. When you reach the same height you started with, the velocity in the y direction is the exact opposite. If I toss the ball upwards with 8 meters per second, it will return to my hand with a velocity of negative 8 meters per second. So that's another trick you can do. Let's see. What's another one? Honestly, as far as solving this problem, it really does just come down to using the kinematics equations. You have to do 2 steps, or you have to do the quadratic formula. There's not too much fun stuff there.
When it says how high does it go, do we have to add the 30 meters?
Ooh, that's a good question. Yeah, the question was, when it says how high does it go, do we need to add the 30 meters? Yes. Now, the nice thing is, the kinematics equations have that built in. So for example, if you decide to use this equation, y final equals y initial plus v initial yt plus 1/2 ayt squared. If you can find the time to the top, you can plug that in and you can find the final height. In that case, your initial height would be 30. If you use a different equation, you may have to be careful. But yeah, its final height better be bigger than 30. Based on the picture, you can clearly see that this height will be bigger than 30. So your answer should reflect that. In general, we measure height with respect to the ground, though, as I taught you with energy, height is all relative. But the general assumptions, we start at the bottom. The last thing, and I think you all know this, remember that the acceleration due to gravity is the same the entire time. If I toss the ball upwards, the acceleration is negative 9.8 everywhere. Once it leaves my hand, it's negative 9.8 every time. On the way up, on the way down, at the top, everywhere in between. So just general, this is good kinematics reminders. 2-dimensional projectile motion problems. We love these problems because they're really easy 2-dimensional projectile motion problems. They're really easy to make. Very straightforward, very easy for you all to understand. Everyone's throwing a ball, very easy for you to visualize. Because one of the things is when we design a physics problem, we have to make certain you can actually understand what the heck is going on in the problem. And this one's very easy to understand what's going on. So, great. That was one of the test 1 free response problems. The other one was actually just kind of like that number 2 that we just did. The multiple choice that we just did. Cars going so fast. Find the force due to the applied force. Draw the free body diagram. All that jazz. So, another of test 1 free response was, to be honest, basically this problem. Like, I'm just gonna, it wasn't this exact problem, but what this problem used skill-wise was basically the problem. Let me see what extra things got tacked onto it to make it different, but the reality is it was basically this for most of it. Okay. So tacked onto this problem was, so this is one part of it. The other part, this was actually part B. Jill passes Bob at a stoplight, and Jill is traveling at 20 meters per second. If Bob is initially at rest and accelerates with an acceleration of 4 meters per second, boom, just delete that part. How long will it take Bob to catch up to Jill? So this is the other free response problem we had to recognize. You got Bob's this is the problem where you had to set this equation, x naught plus v naught t plus 1/2 at squared. Bob, equal to x naught plus v naught t plus 1/2 at squared, Jill. Why? Because their final positions equal each other. So this problem was basically realizing that you could set equations equal to each other. Like this was kind of thinking through. We did a couple of these, and you just did some math. There was a quiz problem just like this as well. So if you are curious about this one, I gave you all a quiz problem like this. Fairly confident there's a problem like this. Just remembering that you can set these things equal to each other. And then part B was if Bob's car was 500 kilograms. So, part B was just doing kind of what we did before. So not too much new to say there. So, and I probably mentioned this to you all. The major concepts from test 1 were kinematics and forces. So the free response problems matched that. The last problem was an entire problem in kinematics. This problem is 50% kinematics and 50% forces. The last problem I gave you all was all forces. So basically, no matter what, you were having to do a kinematics and a force problem. That's the major things you need to know. Circular motion, I reminded you all, circular motion is important. And I think that's people mainly focused on kinematics and forces and forgot about it. So that's, I think, why people missed the other question. All right, and again, I'll upload this PowerPoint, y'all, with all of this. So this will get uploaded to the final thing. Just so you all don't feel like you need to copy out all of this. You're welcome to. It will be there as well. Yeah. Jill is traveling at a constant. To clarify that, Jill passes Bob at a stoplight, and Jill is traveling at a constant, 20 meters per second. If Bob is initially at rest and he accelerates, he has to accelerate to catch up to her. So, good problem. I'm pretty happy with all the free response problems I gave you all, except for there was one problem in the last test that was it was fine. It was the boat and the sails and the wind and stuff like that. No one chose that one. That was not ideal. That one I'll have to go back and workshop. But we'll talk about that one Monday. All right. The last one I actually, so all these problems I reviewed before the test. I think it's called a modified Atwood's machine. Really, really fancy term. Let me just draw a picture of it, because honestly, putting it into words is really tricky. So, test 1 free response, the last one I had you all do, was this. There's a block and a pulley, and the block was hanging from the pulley. This is mass 2, this is mass 1. You were blessed with a pulley with no mass. You now realize that that pulley had mass. It will have a moment of inertia associated with it, and that would actually factor into the problem. So whenever you see in a problem massless pulley, thank your lucky stars, because if it doesn't say massless pulley, you have to consider the moment of inertia of that and the torques and all of that acting on it. That becomes part of your system. You will encounter that, I'm sure, at some point in the future. Maybe, maybe not. All right, so this is the problem I gave you all. I said find A. Find A, acceleration, if no friction. So this one I'll type out. So I first asked you to find the acceleration with no friction, and then I said find the acceleration if there is friction. So part A, find the acceleration assuming no friction. Part B, find the acceleration if the coefficient of friction is 0.2. All right. And there was a trick to, okay, so there's two ways you can solve this problem. I honestly recommend the trick way, where you realize these things are stuck together. These things are stuck together. So you can basically model this problem. So sure, there's a tension going this way, there's a tension going this way, there's a force due to gravity going down here. Eventually, there will be a force due to friction going backwards here. If you realize that these things are stuck together, that string is taut. They're basically stuck together. You can pretend like they're glued together. And all a pulley does, what's the point of a pulley? A pulley takes a force downwards and changes the direction of it. That's why pulleys are useful. I can take something that falls downwards and make it move something left, right, or make something move like at an angle, or make something just move straight up. And a pulley redirects forces. That's what a pulley does. It redirects forces. So to that end, if we kind of draw a free body diagram with these together, I have mass 2, I have mass 1. The tensions cancel each other. There's a tension to the right, there's a tension to the left. They're exactly equal to each other, so they exactly cancel each other. So to that end, there is a force due to gravity that's m2g. If there's no friction, that's it. If there's no friction, that's it. So for part A, m2g is the net force, and you remember, net force equals ma. So m2g equals ma. What is the mass? Looking at this system, the mass is m1 plus m2. The mass of the whole system is m1 plus m2. So long story short, this is literally all you have to do to solve this problem. Mathematically, it's a very easy problem. The hard part is setting it up. But that's it. Really simple. Really just plug the numbers in, solve for A. Easy peasy. And honestly, if you can set that up, the next part is really easy as well. Net force equals ma. m2g, so if we now have friction acting on it, we just do F m2g minus the force of friction equals the same thing. m12 plus m1 times A. What's the force due to friction? That's going to be mu m1 times g. Because this guy experiences friction and the other one doesn't. So, yeah, the trick to solving this, you can set up a free body diagram for each problem and then solve for tension and then do a bunch of stuff. Or you can realize these are coupled together and you can just treat it like one object. And so that's what I drew up top. And the pulley redirects that gravity to make the things move in the way you want it to. They're both going to experience the same acceleration. Because just imagine if one of them is accelerating more. If the bottom one was accelerating more, that would make my string stretch, which is not going to happen. If the M1 was accelerating more, that would make it somehow fly forward and make the string loose, and that's not going to happen either. So anyway, this is it. This is how you solve this problem. Really simple math.
Could you do where you combine the masses? Could you do that if the pulley system, they're both going down?
Yeah. Yeah, it doesn't matter which way they're going. Yeah, at the end of the day, if they're coupled together, yes, the question was, if instead of this, what if they were instead like this? Could you do the same thing? Yeah, you can do the exact same thing. You can couple them together. In this case, they're both contributing to gravity, so it would just be, if I drew this picture, there would be a force of gravity to the left, and there'd be a force of gravity to the right. Whichever one wins, equals m1 plus m2 times A. Yeah. There is some clever trick sometimes in certain problems, but this one is very universal. If things are stuck together, they're going to experience the same acceleration. So think of a car. A car is not one object. I mean, it is. It's one object made of a bajillion small objects stapled together. So the mass of a car is the mass of every single piece of the car added together, and they're all accelerating the same. Hopefully. If they're not all accelerating the same, part of your car just flew off. Everything in your car has to accelerate the same, otherwise you're leaving part of it behind. So, this was the last one. I like this is called, so the one you mentioned, This is called an Atwood's machine. It's such a classic problem, it has a name to it. That's how you know. Anytime a problem's got a name, it's a classic. And it is all over the place in the real world. Elevators, pulleys are super useful for redirecting forces and doing all sorts of things. So, last thing I want to mention to you all, remember gravity affects everything the same. That's the last major point that you all really, really, really need to remember. If you drop a wrench and a feather on the moon, which one hits the ground first? Neither, they hit the ground at the same time. Remember that all things accelerate the same due to gravity. The only thing that affects whether or not something moves faster or slower is air resistance. Really, really, really easy to prove that. You can prove that to anyone in your family, anyone you know if they're willing to listen. Get 2 sheets of paper, crumple up one, make the other flat. They have the exact same mass. Crumpling up a paper doesn't change what it's made of. Crumpling up a paper, the mass is the same. You drop a crumpled up piece of paper and a flat piece of paper, the crumpled up one hits the ground. It's not mass that affects how fast something falls. They have the same mass. You isolated that variable. It's the air resistance. So that's probably one of the easiest way to prove to people that mass has 0 effect on how fast something falls. Air resistance does. So if all the air resistance disappeared on Earth, everything would fall the same. Unfortunately, you all have existed in a world, I say unfortunately, it's actually very good for you, that there's air, so that's a really common misconception that things with more mass fall the same, but it's not true. They all fall the same, assuming no air resistance. Yeah?
So, like, the air resistance and like the friction is like particles hitting each other. So would that be kind of like a momentum problem?
Yeah, so the question was, is a object falling is technically air particles hitting it? Yes, it is a momentum problem. Gosh, I would not solve it as a momentum problem because you have to model every single air particle as a hard sphere and predict which way it went, and that would just be an absolute nightmare. And it's like so many objects. Imagine setting up a momentum problem where you're adding up like 1 billion momentums. Not ideal, but yes, it is a conservation, like momentum is conserved. Yeah. Yeah. So I put M1 and M2 together, so net force equals MA. This M is the 2 masses together. So that, if we look at our picture in the top, that's the one I'm working with. M2G is the only force acting on it. So the net forces, so you add up all the forces acting on something and set that equal to MA. So in this case, what are the forces acting on that thing in the top? Literally only M2G for part A. Then when we get to part B, we have friction, and so I drew the friction arrow for part B. So what I did was I said, what is the, if we look at this picture here, I'm going to delete the force of friction. So any free body diagram problem, any problem ever, the net force equals MA. So you have to draw a picture, and technically, okay, there is FG. Technically, this guy here has FG and FN, but those cancel, so we ignore them. So we say the sum of all the forces acting on it will equal the mass times the acceleration, the total mass times the acceleration. So where did this M2G come from? Where did I get that from? So M2G, if you look at it over here, is actually pulling the thing and making it move. So all I did was I moved that up here. This is the only force for part A, that's the only force acting on it. M2G is the only thing causing that to move. So I drew it on there. So when I add up my forces, that's the only one that exists. So the M2G goes with that, and then the MA goes with that. What is the mass of my thing? The mass of this system is M1 plus M2. So the reason M got replaced with M1 plus M2 is because you could think of this as M net A net. It's the mass of the whole thing. And then the force that was acting on it was just M2G. M1 is not getting, gravity's not pulling it left or right. Yeah, it's a good question. It's a really good question. So yeah, definitely check this out. Make sure you understand what was going on here. Any other final questions, y'all? So that worked out pretty well timing wise. Yeah, Monday I'll do test 2. Monday I'll do test 2, same thing. I'll talk about the problem fuel missed. I already mentioned it to you all before, but I'll remind you of it. And I'll do the response one just because those are like the classic, really important ideas you need to know. I will have office hours Monday, but I will not have office hours Tuesday and Wednesday because there's no classes, and so I won't be here for classes or that. So Monday I'll have office hours, and that'll be my last office hours, y'all.